First, I would like to thank the organizer for this opportunity. The title of the talk is Quantum Walk Dynamics from Classical Interacting Particle Systems. So before starting the talk, I want to place one question. What is the meaning of a quantum state? What do we mean by the wave function psi? There are various viewpoints, for example, many world interpretation, Bohmian mechanics, consistent history approach, and of course there is a totally different viewpoint which tells you that shut up and calculate. But in this talk, we don't want to propose yet another interpretation, but our motivation is more pragmatic. We want to take idea from these different interpretations and make something useful, something of practical importance. With that in mind, let me introduce the discrete time quantum walk system. Discrete time quantum walk state lies in the Hilbert space, which is a tensor product of two space, coin space and position space. Coin space spans by 0 and 1 ket, and position state spans by the lattice points, 1D lattice points. And the dynamics has two ingredients, coin operator and shift operator. Coin operator acts on the coin states 0 and 1 ket. For example, Hadamard coin operation here. And the shift operator moves the walker depending on its coin state. And if the coin state is 0, then the walker will go from n to n plus 1. And if the coin state is 1, then the walker will go from n to n minus 1. And one step of quantum walk is composed of these two operations. First the coin operations and then the shift operation. Now, instead of using the particular coin operation like Hadamard, we can use a generalized form of coin operation, which is a special unitary operator. And this operation is parameterized by these three parameters. And Hadamard coin operation appears as a special case for a particular choice of these three parameters. And different choices of these three parameters gives different quantum walk dynamics. Now, for a quantum walk evolution, we have to take some initial state. Typically, it is localized at the origin. And after operating the walk operator t times, we get the quantum state after time t. And using the Born rule, we can obtain the measurement statistics. And this blue curve shows the probability distribution of a Hadamard quantum walk for this kind of initial state. And this red dotted curve is the probability distribution for a diffusive simple random walk. So you can see the differences. These spikes appears at the edge, which is the hallmark of quantum interference. Now, before going further, let me recall the simple classical random walk, where the particle can go either left or right with equal probability, and the probability distribution is a Gaussian. And we can take a different point of view. And for example, we can take n number of simple random walkers, and after time t, we are interested in the density distribution of these walkers. Then, when n tends to infinity or n is a very large, this density distribution approaches to the probability distribution of a single random walker. And the same thing is for run-on-tumble motion on 1D lattice, where the tumbling rate is alpha. And if we start from n number of run-on-tumble walkers, then after time t, we will get a density distribution, and this density distribution for a large number of particles will be identical to the probability distribution of a single random walker. Now, in this many walker picture, we pose a question that what will happen when this tumbling rate depends on the local density of left movers and right movers. This is the case for active spin models like active Ising models, where these active Ising models are a minimal lattice-based active models which can show collective motions like flocking and phase separations. And this and there is also active pods models also. But here we will propose a generalized version of active spin models. Here we begin with n particles carry spin, and in addition to the spins, they have a extra variable called a phase variable. And this phase depends on the spin state and the position. So for a given position and for a given spin, all the particles share the same phase. And the tumbling rate, here we denoted by R, looks like this. It depends on the local density of left movers and right movers, and also on the phase. And this delta x is like this, where this n tenda looks like this. And here you can see the phases and the parameter, 3 parameters, which corresponds to the parameter of the coin operation, and in the quantum walk. And the interesting thing is, here the phases also evolves with time. And here something interesting appears. And this is the pictorial representation of the dynamics. And if we want to compare the density distribution of this active spin model and the probability distribution of a quantum walk with this initial state, then we have to take carefully the initial condition, the initial density and phases. If we take this initial density and phases, and then we obtain the in the large n limit the density distribution of active spin model and the probability distribution of quantum walk, a similar pattern. And for a small number of particles, we get a classical like distributions. But as n increases, the peaks appears at the edges, which is the hallmark of quantum interference. And for a large n, the difference between these two distributions is extremely small. And if we and these are the trajectories of the particles. And we can also define a Bohmian-like dynamics where the tumbling rate depends on the wave function. And we can compute this wave function from the quantum walk dynamics, or we can compute this wave function from this active spin model dynamics. So, but in the Bohmian mechanics, the wave function guides the deterministic trajectories of the particle, but here the wave function guides the stochastic dynamics of the particle. So this is something different, and this is our work. And there are some recent related study in the literature, and this growing number of study in this direction suggests that the connection between classical stochastic systems and the quantum dynamics is much more interesting than we previously thought. And these are some of our current research direction in this on this work. We are exploring the first passage time of in this model. We cannot define first passage time in quantum walk but quantum dynamics. There is first hitting time. But in this picture, we can define first passage time. We have trajectories, and we are exploring whether this has any connection with weak measurement. And we are also exploring the classical search studies inspired by quantum search algorithm. Quantum walk can do universal computations. So we can also build a quantum global search algorithm using quantum walk. So there may be some classical search studies inspired by this quantum search algorithm. And we also exploring the possibility of a efficient quantum simulation of active spin models. And I sincerely acknowledge Argo Das. And we are exploring this direction together, and we also thank my other collaborators also. Thank you.
Few questions.
Sorry, I might have missed the point, but can you tune your like coin operator to get this classical random walk like distribution even for the quantum case?
Yes, but in quantum case, we have to obtain the classical random walk distribution, right? So you have to do repeatedly measure the walker. But you are talking about can I tune the parameters so that we can get I don't know, but possibly I don't know. I have to think.
Any more questions?
Yes.
So is this, this mapping just holds for the most general kind of
Yes,
quantum walk?
for any kind of discrete time quantum walk.
Okay, I think if we have no more questions, we can thank the speaker and call it a day. Thank you.